Good morning. Today we will continue with the class of ensembles. In particular, we will take a look at debugging and boosting algorithms. To access to the class of today, you can go to the URL link github.com/ericchacon/ensembles tutorial, and you will find this button here, Launch Binder. You can make click and you will access to a Jupyter Lab interface. Okay, we will start with a bugging algorithm applied to regression trees. In this case, we want to study the Boston dataset that contains information about the housing values of suburbs of Boston. Okay, in particular, we will study the median value of owner-occupied homes. We want to predict this based on other variables such as per capita crime, proportion of residential land zones, proportion of non-retail businesses, and so on. Okay, you can take a look at each of these variables. We will use the package mass to access to the Boston dataset, the package rpart because it has the implementation of regression trees, and we will visualize some graphs with ggplot2. This is the dataset. Okay, so this is showing only the first rows, and you can see that we have 14 variables. The last one is our variable of interest. We are going to model this based on the remaining ones. Okay, it is always recommended to do some exploratory analysis. You can take a look in detail of each one of the variables, do histogram, compute summaries, and so on. Okay, so the idea of bugging is that we will have an initial data set. Then we use this initial data set to create bootstrapped data set. So it means just we resample this original data set with reposition, okay? And just gonna, no? And we will have different bootstrapped data set, no? This will be your data 1, data 2, and so on, and data M maybe. And associated to each one of these bootstrapped data sets, we can fit a model. In our case, we will fit a regression tree. So we have our model 1, no, our tree 2, and so on. And so you can see why this is ensemble, because we are obtaining now several models. And when we do our final prediction, for each one of these models, we can have a prediction, no? Prediction 2, 1, prediction 2, prediction 3, and so on. So we can ensemble these values, just computing, for example, the means. It would be where mean predicted value, using all these predictions associated to each one of the models. Okay, so we're going to do this. Initially, the first thing that we have to do is to obtain the bootstrapped data sets. First, we show how to do this with one data set, and then we will replicate. So simply, we just obtain a sample from the indices of the rows of our data set with the same size of our data set, and we add this argument. Is important, replace equals true, because it makes a sampling with replacement. Okay, so here you can see these are the indices associated to the bootstrapped dataset, and these indices, they can be repeated, so there can be rows that appear more than once in our bootstrapped dataset. And once you have the indices, you can obtain your dataset. Here we're showing just the first rows, and these first columns indicates that this first row was the row 1 in the original dataset. The second one was the row 452 in the original dataset, and so on. Okay, so just using the same idea, we can apply this for a certain number of iterations. Here we're applying 100, and we obtain our first bootstrapped dataset, second, third, and so on. Okay, we're just showing for now the first 5 bootstrapped datasets. Okay, the next step is that once we have the bootstrapped datasets, we want to apply a pruner regression tree to each one. So how you obtain a pruner regression tree? Remember that if you apply a regression tree, then you can obtain this complexity parameter table. This contains information about the complexity parameter, the number of the split, the relative error, and more importantly, the cross-validated error. Okay, so you can see that even when you increase the complexity of the model, you have more splits. It doesn't necessarily mean that the cross-validated error is going to be lower in comparison to the training relative error. So that's the reason this is important, because we are avoiding overfitting when using this indicator. So the idea here is that we want to identify this model that has the lowest cross-validation or cross-validated error. Here, for example, we obtain that this is the number 7. And once we obtain that, we want to use the corresponding complexity parameter or penalty to prune our regression tree. Okay, so this is the obtained regression tree after pruning. Okay, so we want to do this for all the bootstrapped data sets. So we put all that in one function and apply this to all the bootstrapped data sets. So you can see we obtain one pruned regression tree, second pruned regression tree, and so on. We are going to obtain 100 of them. Once we have them, we can make prediction. We could make prediction for any profile, but here we are just to showcase, we just choose the first row of our original data set, and we will want to make prediction for this profile. How it works, we just make prediction for each one of our models, and then we can obtain the ensemble predicted value. That could be just the mean of all these predicted values. So here our predicted ensemble value is 26.8, and here you can compare the observed value, the predicted mean value, and the predicted distribution as well. Okay. Next, we can take a look at the boosting algorithm. Here is going to be a classification problem, and we use the HMEQ dataset, which is available on Kaggle. Okay, here our response variable of interest is this variable that is called BAT, because this dataset contains information about applicants for lines of credits. And the value 1 means that they default on loan, and the second, and 0 means that they repaid the loan. So we want to estimate, or we want to classify profiles based on the amount of the loan, the value of the current property, and so on. Okay, so in comparison to the previous notebook, we also need here the package ADABAG, because it has the implementation of the boosting algorithm. Here we are just loading the dataset. Again, you can do some exploratory analysis. I recommend it. And here something different that we do is like we do a more proper split of the dataset. No, so usually the dataset you could split in 3 groups. Okay, and the training dataset, the validation dataset, and the testing dataset. The idea here is that this testing dataset, you don't touch it while you select the models, while you select IP parameters. You just use at the end to inform about the results of your model. Okay, so we are going to doing that here. And so for that, we just obtain the indices for each one of these datasets, and we subset each of these datasets, and we obtain the training dataset, the validation dataset, and the testing dataset. So first we apply a classifier decision tree, because we want to compare our boosting algorithm with this decision tree. Okay, we have all the information. Take a look at this initial error, which is the proportion of misclassified cases. And then we are going to apply the boosting method, which is implemented in the ADABAG package with the function boosting. Here, okay, something important to remember is that the boosting method, what it makes is it is a sequential algorithm that puts some weights on the observations, and it adapts the weights depending on how well we are performing on predicting or classifying the profiles. Okay, so it's gonna iterate That's the reason it has this argument and final, which is the number of iterations that we want to adapt these weights. And finally, you can provide also some additional hyperparameters related to the decision tree in this case. Okay, so for this boosting model, we obtain the confusion matrix, and also we obtain the error, and you can see the error is lower than this initial error using just a decision tree. Okay, you can also take a look at how the error evolves. Remember that the weights are being adapted depending on how well the model is performing. And finally, we can test our selected model on the test data that we didn't use before. No, take a look. The error is low as well, so it looks like we are not overfitting the original data set. Finally, I want to show another way also where we use now cross-validation. Here the idea is that if you have the original data set, actually what we know is good to do is that we split this into a testing data set and a training data set. The testing data set we are not going to touch again until the end, but the training data set now we can split in k faults in such a way that for this fault we are going to use this to validate the model, fitting the model with the remaining faults, and the same for the second fault and the third, and so on. Okay, so this is just the small variation that we want to do. We add now the package caret because it allows us easily to create these faults. We're working with the same package. We were saying with the same data set about lines of credit, and then here the first step is that, as I said, we split into the training and the testing data set. Okay, and here is the training data set, the testing data set, and then the next step is that we create the faults. Here we have the faults that we are going to use for cross validation. They are just 10 subgroups from the original training data set, and then for each of these faults, look, we identify the IDs for each fault, and then we say for the fault E, the validation is just going to be exactly this group of the subgroup, and the training is going to be just the complement. Okay, so once you have this, then you can apply your decision tree, you can apply your boosting algorithm, or you can apply any other model, and you are going to compare them using cross validation. So we are showing here the errors associated to the decision tree. Here are the errors associated to the boosting model. Remember that we have 10 errors because we have 10 faults. And of course, if we want to summarize, we can obtain the mean error for each method. And for the model only using decision trees, look, the mean error is higher than with our boosting algorithm. Okay, so the boosting algorithm is performing better, and of course we can use this algorithm to evaluate the error now on the testing data. And take a look, the error is small. This is an indication also that we are not overfitting the data. Okay, thank you very much for your attention.